Hi, everybody. This is Liz Stanton from Synapse Energy Economics, and we're here in Cambridge, Massachusetts, getting ready to start our webinar on a guide to electric sector modeling tools. I'm a principal economist here at Synapse, and I'll be moderating today's talk. I have with me Jeremy Fisher, who is also of Synapse, and also joining us today in our Cambridge office is Fernando de Cisternas from Argonne National Laboratory. I'm going to start off by just going over some of the logistics for the call, and then from there I'll turn it over to Jeremy to begin the discussion. So if you haven't joined us on one of our webinars before, here's just a quick introduction to how we do it. Everyone on the call, except for the presenters, is going to be muted throughout the call. Your opportunities to ask questions then are not by speaking them aloud, but rather by sending them to us. If you're having any kind of technical problem, please use the chat function in the WebEx software. You can see a chat in the screen that you're looking at now to ask us to help you out with solving those problems. If instead you have a substantive question, a question that you'd like to have the presenters answer, or something that you'd like to see discussed, then I'd like you to send those questions to me at webinar@synapse-energy.com. I'm going to be monitoring that email address throughout the talk today, but most likely I'll save all of your questions for the end, and then after about a half an hour of presentation, we'll move on to getting those questions answered for you. That is about it for the logistics, so I'll turn it over to Jeremy to get started.
Thank you very much, Liz. This is Jeremy Fisher at Synapse. And for those of you who don't know Synapse, we're a small consulting firm out of Cambridge, Massachusetts, as Liz was just noting. We're a firm that works primarily with public interest and public sector clients. We work for federal agencies, state agencies, regulators, environmental advocates, and consumer advocates across a variety of electric sector issues. And we've been engaged with the Clean Power Plan since pre-proposal for a number of clients, including regulators and interveners in various cases and those who are interested. One of the things that we've noted over time is a fair bit of discrepancy about how different parties think about modeling for the Clean Power Plan and for other types of resource planning. So that's going to be the basis of today's discussion. And I am joined today and in the paper that accompanies this webinar with Fernando from Argonne National Labs. Fernando?
Thank you, Jeremy. My name is Fernando de Cisternas, and I'm an energy systems engineer with the Center for Energy, Environmental, and Economic Systems Analysis, or as we like to call it, CEEESA, at Argonne National Lab. Most of us are located at Argonne outside Chicago, and our group uses a systems analysis approach using state-of-the-art scalable modeling tools based on techno-economic optimization and agent-based models. And the research that we're mostly working on is, well, concentrates on the most pressing issues relative to the system-level integration of energy resources through power systems analysis, energy systems analysis, as well as environmental systems analysis. And I'm going to turn it back to you, Jeremy.
Thank you. So today's talk, if you've looked at the paper so far, then you'll know that the paper is moderately technical, and today's talk certainly sounds technical. We're going to try to make modeling a little more fun today to the extent that that can actually happen. But this is driven by a number of questions that came out of both the Clean Power Plan and the way that states were thinking about the Clean Power Plan, and the way that we think about modeling and different types of approaches that you can use for thinking about how your state or utility is going to work within the construct of both the Clean Power Plan and other generally compliance obligations for state planning and utility planning. So here's our general sort of motivation. I've got a question of how am I going to go ahead and meet growth while thinking about hitting my energy efficiency and renewable energy targets, meeting environmental constraints, and I've got to assess the least cost compliance path for environmental regulations. But if on top of that I'm also planning for the Clean Power Plan, I'm asking these questions about whether I should go rate or mass. Should I auction or allocate my allowances for part of that? On what basis? And who? Who's going to get those allowances at the end of the day? And with whom should I trade? And how will all these choices affect my operations at the end of the day? It's a lot of questions that all have very, very different approaches. If I'm in the process of conducting another type of resource plan that's not necessarily connected to the Clean Power Plan, how am I going to take into account what my neighbors are doing? How am I going to think about retiring resources, fuel price uncertainty? And at the end of the day, in almost all of these processes, whether it's a utility process that's disconnected from the Clean Power Plan or specific to the Clean Power Plan, we have stakeholders. We pretty much need them too for just about every regulated process, and even in non-regulated processes, they're a healthy component of doing good sustainable planning. So overall, there's really no single model or analysis structure. There are different types of models that can get used for different purposes. So the purpose of today's call and this webinar is to walk through the range and spectrum of the analysis types and model types that can get used for long-range planning. Since this was originally billed and continues to get billed as a Clean Power Plan based modeling paper, but I think is actually really more expansive than just Clean Power Plan alone, we're going to start off with just a brief description of what the Clean Power Plan requires for performance demonstrations, and a brief discussion of how this fits into that particular rubric. And then once we're past that, we're actually going to leave off on Clean Power Plan for a while and pick it back up at the end. Think about considerations in choosing an analysis overall, different types of analysis trade-offs that the different types of models present to both state agencies, reviewers, and utilities, and then walk through the range of models that we're thinking of, which are production cost models, capacity expansion models, multi-sector models, and non-optimization approaches. By the time you're done with this webinar today, while you certainly won't be necessarily an expert in those, or I don't expect you to be, and there is no quiz, you'll at least have a sense of what the different trade-offs and positives and negatives are of those types of different approaches. And then I'm going to spend a couple minutes going over example analysis pathways, and this would be both applicable for Clean Power Plan as well as for other utility planning processes, and then some brief conclusions. So briefly, to give us some exegesis within the Clean Power Plan, for those of you who have joined us for other webinars previously or have seen others of our work on the Clean Power Plan, we think of the Clean Power Plan as having two basic structures of rate-based compliance and mass-based compliance. This is the same way that EPA has structured Clean Power Plan compliance options. And within those, there are a number of different pathways that states can choose to take. Most of you are well familiar with EPA's construct of within rate-based compliance, subcategorized CO2 emissions rates versus state average CO2 emissions rates. EPA also leaves open the door for states to come up with their own category of emissions rates, as long as the overall emissions at the end of the day come out on a rate basis under the state's target. But in doing so, the state needs to provide a demonstration to EPA that the mechanism that they've chosen is going to successfully come in under EPA's targets. And that's being called a CO2 performance demonstration. Separately, under mass-based compliance, states are welcome to take a presumptively approvable approach of either choosing a mass-based goal for their existing units that's trading ready, or a mass-based goal for their existing units with new source complements that's also trading ready. And for those, EPA does not require any substantive form of demonstration. However, if a state chooses to take a state measures plan, then there are performance demonstrations that are required under the rule construct by EPA. EPA has not provided very much guidance as of yet in terms of what they would necessarily deem acceptable or unacceptable, but there is language within the preamble and within the rule itself about what types of aspects of that analysis EPA expects to see to show that those demonstrations have been rigorous and comprehensive. And so when a state is considering state measures plans or a rate approach with different CO2 rates, that's where this becomes a legally required mechanism. But under almost any approach that a state chooses for clean power plan or for any other type of planning, this is all relevant regardless, and it's probably still a good idea for a state to pursue some level of fairly significant modeling and planning when thinking about the level of dollars that are on the line at the end of the day. So states have a number of considerations to think about in choosing an analysis. Your analysis is going to possibly need to represent a whole variety of different types of issues, from the markedly obvious of having a market-based emissions reduction approach in your analysis and that your analysis can actually represent, all the way to some things that are slightly more subtle. What are the impacts of your renewables and energy efficiency in your system? What resources are displaced by those? Is it reasonable to expect that it's fossil resources in your state, or is it somebody else's state? How are you going to go ahead and model that? Do you need to be worried about transmission constraints in your system? Do you need to be worried about what's happening in other states and how actions that occur in other states impact compliance in your own state, or just impact costs in your state? There are fundamentals of the building blocks that might be useful for states to consider if you're going on a clean power plan direction, of thinking about efficiency improvements for EGUs and generation shifting and emissions limits that all have different impacts on the overall system and possibly require some more in-depth modeling direction. And then there are just fundamentals of good modeling approaches, which is transparency and openness and auditableness. And all of these run up against, at the end of the day, computational requirements, transparency, and then the requirement for the use of expert modelers. So at the end of the day, there are a lot of requirements for what you're thinking of when choosing an analysis. Moving on to this table that looks incredibly busy and is, but this is going to be for more future reference and describes sort of the dimensions of the things that we think about when we're thinking about the different types of modeling approaches. So in a couple moments, I'm going to be describing what a production cost model is versus a capacity expansion model at two different types of scales and also multi-sector models. But some of the fundamental questions about those models and non-optimization approaches is whether they can handle dispatch in the first place. Most modeling approaches do have some form of dispatch. This is the question of the least cost resources being brought online prior to less economic resources in a merit order direction. Okay, well that's fine, but do the models then also consider chronological dispatch and unit commitment? These are the questions of units that must remain online once they're brought online, or must remain online for a certain amount of time, or offline for a certain amount of time, or have constraints in how quickly they ramp. And there are only a limited subset of models that actually take those considerations into account when they're also considering other factors as well. Once you're thinking about that scale of depth, does the model take into account multiple and regional scales? Is it across multiple states, or is it specific to just your utility? And different types of constructs have a different ability to be able to have that trade-off. On the opposite end of the spectrum, the broader the scale is of your model, the less able it is to necessarily take into account specifics of individual units. So there's a trade-off of the larger the expanse and scope of your model is, the less likely it is to be able to take into account the specific details. Then a completely different class of model from production cost models, the capacity expansion models, also have the ability to choose new resources and retire non-economic resources. And all of those have their trade-offs and opportunities, but all of them require a fair degree of expert use. Over here on the far right side of this column, we also see these non-optimization approaches. I'll be describing those as some purpose-built models that across the board don't require expert use, are fully auditable by the public and use public data, which is not really common to the other classes of models that we'll be discussing prior to them. One way of generally thinking about the models that we'll be talking about today and this non-optimization approach is across this spectrum of at least two dimensions of complexity. And one is its approximate model spatial scale, which is along the x-axis of this graph, going from utility scale to global scales. And the other dimension is how specific and the level of detail gets on unit operations. And so at the very most detailed, it's specific operations of individual EGUs on an hourly to minute basis. And at the most general scale, the broadest spectrum, it's generic technology types not specific to individual EGU, possibly not even specific to costs at specific locations. And so there are very fine-grained models of production cost models that can cover both a fairly broad expanse and high level of operations, but don't cover the national or global scale. And then at the other end of the spectrum are these regional capacity expansion models and multi-sectoral models. There are other fundamental differences between these two, but this gives you a sense as to where those fall along the computational threshold and why there's that trade-off. So I'm going to start off with production cost models. And here's the trite example of why you want a production cost model. Keep your eyes open for these trite examples. This helps me think about the way that these different models are also useful, and hopefully it helps you as well. Yeah, in this particularly trite example, about 100 people who need to get from Boston to New York in 2 days with 4 different cars. I've got a bunch of different cars, an old van, a small sports car, really fast, a slower hybrid, really fuel-efficient electric car. How should I arrange the trip so that I can get the most people through fastest with the least cost? Well, I can use something like the construct of a production cost model to figure out the best way to use those specific 4 cars to get people back and forth real fast. So production cost models are designed to determine the least cost dispatch of a known set of resources. That is, I've got a specific fleet, and now I need to know how I'm going to dispatch that fleet on an hour-by-hour basis. On the left side here, you see a graphic of, in this case, it happens to be Michigan's dispatch in 2014 over a week in August, and it just shows the individual hour-to-hour output of individual units in Michigan, in this case color-coded by their CO2 rate, and so you can see units ramping up and down, units that are more economic staying online longer, and units in this case that were less economic coming on during peaking periods. And a production cost model is designed to figure out exactly when individual units come on and off. These are really useful for hourly market prices, fuel consumption, actual dispatch. This is the similar construct to what utilities and ISOs actually use for the purposes of dispatching their systems. And for commercial everyday use within utilities and states, there are a couple of models, ProSim, Plexos, GenTrader, Aurora, GE Maps, that are familiar to utilities and states. The next class of model moves in a completely different direction and asks a completely different type of question. These are the regional scale capacity expansion models. So now we're going to take that same trite example we had before of getting back and forth from Boston to New York with just 4 cars, and we're going to change the question altogether. Now, 10 years from now, not now, I expect that the transportation demand will double and gas prices will be higher across the entire region. Should I be investing in the regional rail system? It's a completely different class of question. It doesn't ask questions about how the units that I have actually operate today. It asks more about how I should be directing my long-term investments. So things like AEO, the IPM model that's used by EPA for looking at the costs of different policies, are all versions of these regional scale capacity expansion models. Generally, they're used to determine the least cost technology type build out under different policy and economic constraints. They have a very low temporal resolution and a fairly low spatial resolution. They cover a broad range of area, but they're not necessarily specifically unit specific. And they also step back on the way that they handle dispatch so that it's not as highly specified, but uses a larger supply curve dispatch. These types of models are used to forecast fuel trends and consumption, technology types of development, policy impacts, and generally long-term expectations. And you will have run into these in, again, EPA's regulatory impact assessments when EPA uses IPM. That's a construct of this model. When you look at the annual energy outlook from EIA, that's using the NEMS electricity market module. Also reads from NREL and Haiku from RFF are versions of these models. This is not meant to be comprehensive. Scaling down, one can go from that regional scale down to the utility scale, which is the question of what do specific utilities look at when they ask questions about their own individual units. And so we can scale down from this larger regional scale model plant technology types down to individual EGUs and go down to this utility scale version of the capacity expansion model. It's got a narrower geographic coverage, but much more specific information about individual units and individual transmission lines. So now going back to that trite example, instead of looking over the course of the next 10 years and asking about my regional transit system in general, I'm going to take that trite example and I'm going to say 2 years from now I expect to transport 120 people in 2 days and my van is broken down. So do I repair the van or do I buy a bus? Right? It's asking now a fairly specific question about information that is specific to my system. It is not asking about more general regional trends, but it's asking about something that I should be looking at out in the future rather than today. And it's making long-term decisions. And in this case, the graphic that we see over here is generation in Michigan again, but this time, instead of looking at generation over time from the annual energy outlook, that broad-scale, regional, generic model, it's now looking at individual units within Michigan within a model called System Optimizer. This is modeling that we're actually doing for Michigan State right now for Clean Power Plan compliance purposes, and looking at the generation of individual units over the course of a 20-year analysis period. And so it asks a similar series of questions as the regional scale capacity expansion model, but on a much more specific question. This is the type of tool that's used by utilities in making resource choices, in doing integrated resource planning, in trying to decide whether units should be retired or retrofit. It is common to see in fairly recent regulatory structures within the utility world. Finally, there's this class of model that I'm calling the multi-sector model. These are the models that try to take into account what's happening across different sectors. How does the electricity sector impact the transportation sector, and how does that impact the demand sector, and how does overall economic activity impact all of those? And so this tries to tie together both modules for fuel production, energy consumption, energy production. These are very, very broad-scale models that tend to ask very general types of questions, yet try to take into account a lot of information across a lot of different sectors. So they're clearly not asking questions about individual units. They're asking questions about a broad, generic set of technologies. And there are, the entirety of the NEMS program that's used by EIA for AEO is a version of this. There's also MIT's EPA and Markal model that was developed by EPA for these types of purposes. And these tend to get used to look at the impact of policies across sectors and also academic research. Finally, we have this class of models that aren't really models at all. These are non-optimization approaches. And these are a class of model or a class of analysis that is not particularly easy to define right off the bat. These are types of approaches that tend to be purpose-built. And in this case, I'm going to be talking about purpose-built screening tools that have essentially simple simulations and bookkeeping in them. The purpose is to be transparent, user-friendly, answer specific questions, and be accessible to stakeholders. So one such example of a non-optimization approach for looking at clean power plan planning is, in fact, the Clean Power Plan Planning tool built by Synapse. This is one of several types of tools that allows users to interact with the energy system of Michigan, in this case, as this or any other state that they happen to have chosen, and look at how different types of compliance options, such as energy efficiency, renewable energy, plant retirements, redispatch of particular units would impact their state and possibly other states as well, and give a rough estimate of both costs and opportunities for compliance. It's not a dispatch model. It's not doing its own intrinsic capacity expansion, but it does have high value for end users to be able to at least explore the system. And in this case, this happens to be amongst a class of other models that are similarly structured. MJ Bradley has one, the Clean Power Planning Tool. In this case, Energy Strategies has produced one recently, the 5-state tool that's supposed to expand to the 11-state tool in the West. And ACEEE produced Super and most recently Super 2. All of these are designed to allow stakeholders to readily engage in clean power plant planning with their state and their regulators. Again, these are not tools that have an optimization component, but they're freely available and easily accessible. So this raises the question of, given this huge spectrum of tools from multi-sector models that cross the whole U.S. to possibly the globe and take into account these broad pathways and multi-sectoral components, down to utility-scale specific capacity expansion models and through production cost models, what is a state to do? How are you supposed to actually think about this, and which models are actually accessible to you? And one thing that you'll hear from states is that these models are expensive. Aside from those screening analyses that are produced for the purposes of allowing stakeholders to be directly engaged, the use of these models can get both expensive from a licensure perspective as well as the expert use and production of those models directly. So I'm going to give a couple of examples here. Let's imagine that we are looking for broad stakeholder engagement, but we ain't got no budget. So we're going to harness our screening analysis. This is one of those 4 types of purpose-built models, CP3T and the other types of screening tools. And this is a possibility where we harness that screening analysis and we get an opportunity to vet it with stakeholders and utilities. We get a lot of wide engagement out of that, but we're not necessarily going to represent real policy outcomes or behavior. So it's got some pluses and minuses. And we might really overrepresent the ease of compliance by using a screening analysis alone. So now let's imagine a system in which we have a state that has the ability to use the utilities models, or the utilities are willing to do modeling on behalf of the state with the imagined situation that you actually have stakeholder control over the assumptions and portfolio choices and compliance routes. How should a state think about handling that? Well, here's an opportunity where you can begin with that screening analysis and then pass options from that screening analysis over to a production cost model to actually see how that model interacts with your screening analysis. This has the distinct advantage of giving you operationally sound outcomes. If the production cost model is successfully solved, it's quite likely that your system is actually going to work and give you costs that are consistent with the way that the utility actually works. It'll capture economic shifts. If you implement something like a CO2 price, that will actually be reflected in the way that units dispatch. But on the con side, it's not necessarily going to capture the economic portfolio development. You're not necessarily going to get a least cost solution. Moving sort of up a notch into maybe your opportunity to use models that are a little bit better suited for the job, maybe you have the opportunity to engage with a utility scale capacity expansion model. And this, now you have the opportunity for a proprietary model, but you still require some amount of EGU specificity, either for wanting to know how stakeholders are going to actually react to looking at specific units and how those units are impacted, or you want to report something to EPA that has that unit specificity. So in this case, you can begin again with that screening analysis, pass it over to utility capacity expansion model. And here you get a really detailed analysis. You're looking for a least cost solution. You're identifying your impacts at specific EGUs and allowing for unit retirement and new unit building as compliance options. Those are all great. But because of its narrow scale, you might not actually pick up interstate impacts or wide allowance trading. And because these kinds of things tend to be expensive to run and operate, you might have a limited number of runs available before you just run out of budget. At the end of our list here is the opportunity to work with other states, couple your analyses together, gather some economies of scale and look for multi-state solutions, which in this case is using a regional capacity expansion model. And this is the possibility of testing your compliance options through that regional capacity expansion model, and possibly predating that with a screening analysis and possibly passing it over to a utility capacity expansion model in order to really get the specific information that you're looking for. This gives you a pretty comprehensive analysis that looks for a least cost solution. In this case, this possibly does require 2 proprietary models. But at the end of the day, you're getting a lot of information about how the other states around you are going to react, how those states are expected to interact with your states and your utility, and how your individual units might actually operate within your system. At the end of the day, there are a lot of considerations to be had between trying to choose throughout this suite of options and what works for your state, whether it's for clean power plan or integrated resource planning or any other form of utility planning. Screening models that are out there are freely available. They're a really great option and probably should get harnessed by most stakeholders looking to get engaged and at least open the discussion in the first place. There is a note of caution that they might contain significant undocumented implicit assumptions. It's worthwhile approaching with a grain of salt and at least understanding what you're using and what those outputs really mean. And I think, can't really stress this enough, but states might want to carve out space for utility scale models that really can create plans that are cost effective, equitable, and achievable. States will point out that the cost of these models and these proprietary models can be quite expensive, but overall that really pales in comparison to the expectation of what the cost transfers and revenues of this overall system will be. It's worthwhile using a model that really gets down to the bones when dealing with something that's going to be as systematically important as something like Clean Power Plan or other large environmental compliance obligations. Seek cost sharing and leverage those utility models, and look for opportunities to create cost-effective regulation. So with that, I'm going to actually close out this presentation right now, and we'll take questions.
So you see in front of you the webinar at synapse-energy.com email address. Please use that to send your questions. I've already received questions from a couple people, and I'm going to get started with asking those of the presenters. So thank you so much, Jeremy, for that very helpful presentation. I'm going to be asking questions that hopefully both of our presenters today can help us out with answering. First, you presented a lot of different kinds of models here. There's so many options that exist. Let's say for a moment that I, like maybe many people that are listening, I want everything. I want a model that will do everything for me. I want to be able to have my economic dispatch. I'd like to see the long-term capacity expansion. And I'll ask you this question 2 ways. I mean, obviously, what should I do? What can I do that gets me everything? But one, sure, I probably also have budget constraints, thinking about how much time and money I have to spend. So maybe answer it for me in a real world like that, where I have constraints, and then answer the same question for me. Is money and time are no object to me? Is there something that can do everything?
Well, thank you, Liz, for the question. What I can say, first of all, is that with modeling, the short blanket theorem applies, right? You have a very short blanket, and it's very hard to cover your head and your feet simultaneously. So you have to decide. And typically, what I would expect states to go for is to multiple classes of models, depending on the time resolution that they would like to include, and on the time scope that they would be interested in adding to their results. What I would expect is that, as Jeremy was mentioning during his presentation, the states would start by doing some screening modeling to see what are the different available options, then to run some capacity expansion planning to understand what are the optimal combinations of those options to supply the future growth of electricity while complying with Clean Power Plan requirements. And finally, running some production cost model, because one characteristic of capacity expansion models, or at least commercial capacity expansion models, the ones that are up there, is that they guarantee the optimality of the solution. You're going to have the most efficient, the most cost-efficient solution to supply your electricity, but it doesn't guarantee that your solution is going to be technically feasible. So you have to run this production cost model with the resulting plant mix from the capacity expansion to make sure that that energy mix can actually supply demand instantaneously, and at the same time it can comply with all the technical constraints of the units, because remember that in power systems, kind of like the overarching requirement is that you have to meet demand with generation instantaneously. And if you have a lot of renewables, and renewables are intermittent, then you need resources that complement those renewables, so that together you can supply electricity instantaneously at minimum cost. And these units are physical assets, right? So they cannot increase their production really, really fast. Some of them can, some of them cannot. So you have to account for all these differences between different technologies and introduce them in your models to guarantee that whatever solution you come up with would actually work in reality.
Yeah, I think that's generally right. I guess I would couch it in saying that I think some of the responsibility in running the production cost model to test the options that have come out of a capacity expansion model possibly reside with the operator of the electricity system, in order to be able to provide a positive dialogue back to the regulator to make sure that the compliance options that they're pursuing are actually going to be pragmatic. I think in a number of states, the way that you're looking at this compliance planning from the state is not necessarily in a way that's going to dictate the precise outcome of the electric system, but asking the question of, if we apply the following policies, what is a reasonable expectation for how the system might evolve? And in those cases, I think it's reasonable to get up to this point where you see that a system is viable or close to viable, and then fine-tune the remainder of that with the utilities expertise in order to really answer the questions about operability and instantaneous power.
And is there a way in all of this that I can kind of get the most bang for my buck? If I have a limited budget, maybe, it's not no budget. I don't have to stick entirely to the pre-screening tools, but it is limited. Where should I focus my resources?
I think there's a huge opportunity for states to team together large opportunities at scale to be able to pool resources across states, both because you get the opportunity to look at a larger scale model that takes into account multiple states' considerations simultaneously at approximately the same cost that you would otherwise do that for a single state. But you also make sure at that point that you're taking into account policy considerations and operational constraints that matter to those other states that don't necessarily matter to yours. So I think states looking to do this together makes a lot of sense.
I absolutely agree with that.
So when we're talking about doing modeling that's going to be relevant to Clean Power Plan compliance, there are a couple moments of that. There are some ways or some particular pathways for compliance where you might need modeling during the planning stage in order to do a demonstration. But also down the road, is there also a possibility of modeling out in the compliance years? Or are we talking about compliance needing to do modeling at those different moments?
Yeah, so I think there's certainly the distinct moment in the near term, which, regardless of which direction we look at the stay, for states to figure out their compliance pathway and which of the compliance pathways they're going to choose in the first place in order to be able to submit to EPA, whether or not it's one that actually requires a performance demonstration. Right? Obviously, if it's one that requires performance demonstration, EPA has specific requirements for those. That must be submitted as part of that demonstration, but otherwise just even choosing which compliance pathway you're taking and which policies you're going to enact. as you go further downstream, I think it's incumbent on states to continue doing forward-looking planning in the same way that state energy offices have done, in the same way that states that look at integrated resource planning have done, to ensure that their policies continue to work forward, but I think it has a slightly different meaning than this singular moment that we have right now to actually choose a compliance pathway.
Mm-hmm. And so as we're looking forward, first during this planning period, which will last at least for the next couple of years, maybe a little longer than that with the stay, we don't know yet, and then thinking out into the later years, what should we expect to see in terms of how these tools are going to change over time?
Well, I can take that question. I mean, we've seen a lot of change in the last few years, computationally in particular. Just think about how things were done before. Planning tools were only based on economics, were mostly based on economics, and they were only exploring the trade-offs between fixed cost and variable cost of different generation technologies. They would have plants with very high fixed cost and low variable cost like nuclear power, and then plants with low fixed cost and high variable cost like gas. And that simplifies the problem a lot by just focusing on those characteristics. So the way in which I expect these tools evolve in the future is for planning tools to incorporate some of the features that production cost models have now, and some of the technical detail that are exclusive now to production cost models, so that these planning tools are more realistic, and not only they guarantee or they give you an optimal solution, but they also guarantee that the solution that they give you is also feasible. So incorporating all those technical details, as well as, for instance, the need for reserves. As you know, renewables require the system to have some reserves in case there's some imbalances in your forecast, differences between what you forecast that you're going to produce and what you actually produce. And the system has to be ready for those imbalances and to act upon them, increasing the output of other units that are non-renewable that the system might have again, to meet instantaneously electricity demand.
Mm-hmm. Jeremy, did you have thoughts too?
Yeah, I actually look at this from possibly the non-technical standpoint of what I would hope to see incorporated into these types of modeling efforts going forward. And I think of it actually from the perspective of data sharing. And one of the things that we see in some states, California is a great example of this, of a state that develops its own publicly available data package that can get used by both stakeholders, utilities, planning agencies, both the environmental planning entities of California as well as the operational entities of California, is a Western-wide data set that they use for the purposes of figuring out long-term and short-term planning. And so I don't know if this is an expectation of what we'll see or a hope of what we'll see, is as we start getting something like MISO has expanded in size, we now have other balancing and trading areas that are continuing to expand outwards, that as those marketplaces and central balancing authorities expand outwards, that we start to get a better sharing of data within those structures that allow us to do more comprehensive interstate planning. And I think that will become more important as we start getting larger amounts of renewables and different variants on the system.
Mm-hmm. So just to remind everyone, if you have a question, please write it into webinar@synapse-energy.com. I do have a number of questions here that people have been sending in. One of the ones that I got was asking for some kind of resource summarizing the information that you're giving, looking at the different categories of models, their characteristics, and then also with that, what are the examples of the models? Am I right in thinking that there's a table like that in the report? Can you tell us the table number? So you'll see on the Synapse website, there will be the slides. We also are going to have the audio for this presentation, and we'll be sending around the slides and the audio to everybody that's on the call. But also up on our website is the report. Go ahead, Jeremy.
That's right. And the report, the first table of the report on page 7, has a fairly simple, straightforward summary of some of the main features of these models and does give a brief description of what the models are that you might recognize out there in the marketplace, as well as Appendix B, the very last page of the report, gives a reference for each of the primary models that we reference in here, where you can find out more information about those specific models.
Okay, that's really helpful. Thank you. So can you run through for us for the various kinds of models and examples of models that you've been talking about, to what extent and how do each of these let us know the emissions implications of generation? So certainly for CO2, maybe for other kinds of pollutants as well. What can these models offer us there?
Well, what I can say is that most, if not all, of these different classes of models incorporate some capabilities to assess the emissions, right? They all are going to tell you to some extent the output of the different power plants in the system, and each different power plant is going to have some emissions associated with it. So all of them can give you an assessment. Now, the degree of the accuracy of that assessment will vary depending on the kind of model that you use. So, for instance, with a screening model, that assessment is going to be very rough, and you can have a first understanding of the extent to which different options might comply or not comply with a clean power plant, and that might allow you to eliminate some options that are obviously not valid. But then you want to go one step further and use some of the more advanced tools that make a more accurate assessment of what those emissions are. Maybe Jeremy.
Yeah, it also depends, I think, to a large extent on how the model has been populated. If a model has been populated with an eye towards specifically being able to characterize emissions well, all of these models, as Fernando just noted, have the ability to output emissions and output emissions implications of any of your compliance actions, both for CO2 as well as generally for at least NOx and SO2, and some of these models even have the capability of going above and beyond that into mercury and particulates and other types of emissions as well. But again, it depends on how the model has been populated. If the model, either user or data set provider, has taken care to get that level of specificity, then you'll get quite a lot of information. I would note that when it comes around to specifically NOx and SO2, because that's so specific to individual units, you lose a significant amount of that resolution when you grade up to non-EGU specific models. And that starts becoming a much broader characterization rather than the specifics of where NOx and SO2 emissions are actually coming from.
But there's less of that failing for CO2, am I understanding?
It's less of a problem with CO2 because it's more directly attached to your just fuel type.
Mm-hmm. Okay. So leading off from there, one of the questions that we've had is about how can we connect the kinds of electric vector models that you're talking about to air dispersion or air quality modeling. Maybe you could quickly explain for those on the line that don't know what dispersion or air quality modeling is.
Oh, that's a great question. So air quality modeling are the models that are used by the air districts and departments of environmental quality and EPA to determine what the atmospheric impacts are going to be of emissions from both stationary sources and mobile sources. So when assessing compliance with national ambient air quality standards, dispersion models are the class of models that are used to figure out how point source emissions translate into impacts downwind. And up to now, I think there's been a moderate amount of connection between those two. EPA very much connects those two types of models through the use of IPM and in its regulatory impact assessments. So when thinking about what types of costs are going to be necessary in order to achieve a national ambient air quality standard, EPA will connect IPM outputs to a class of models that do air dispersion. There have been a couple of other primarily academic efforts to connect more high-resolution models to air dispersion models, but it's quite a lot of hardwired coding that requires in order to be able to have it happen. We have a model that we produced in conjunction with EPA called AVERT, the Avoided Emissions and Generation Tool, that is specifically tuned to allow states and entities to figure out what the near-term avoided emissions impact would be from renewable energy and energy efficiency, and then has an output where a user can just select, export this to an air dispersion model through smoke format, and it's a one-step process. But I think that's actually fairly rare within the energy modeling world.
Great. So kind of a similar question about connecting these models to other sorts of models. This is a question about connecting the electric sector models into other kinds of economic models. There are various models out there, so a good one for you, Fernando, to talk about how can we connect in from these kind of results to models of the broader economy. Right.
Well, there are some models out there that model how different sectors interact with the electricity sector. Now, usually the level of detail that these classes of models introduce is relatively low, or I would say it's very low, and you can have an idea of what the impact among different sectors are going to be, these partial equilibrium models or general equilibrium models. But at the same time, that's not going to include, or it's going to be very hard to include the particularities of all states' policies or the different cost structures of the units. So as time goes by, this will obviously evolve and will obviously improve. But right now, the resolution in which the electricity sector is included in these class of models, I would say, is relatively low.
Mm-hmm. Yeah, and I'll add in that there are different kinds of economic models out there and different ways that we can connect to economic models. So in addition to the kinds of broader economic models that Fernando was just talking about, we also, for example, here at Synapse, sometimes connect these sort of modeling results to in-plan modeling, and there are other similar models to in-plan out there that other folks use where we're thinking about what are GDP effects or what are from there job effects. And there's lots of ways in which it's quite generalized, but it gives a first-order impression that can be useful, right? And that sometimes connecting to those input-output analyses can be useful and is often used at kind of state and local level planning efforts. So.
Yeah, that's absolutely right. There's different inputs that you can use in these models too. That's another way to include all these macro effects that the economy might be experiencing on these modeling tools, and that's definitely one of the simplest way to account for all these effects. Now, when it comes to understanding all the different relationships, then you will have to go to one of these general equilibrium models or these partial equilibrium models that might give you a better idea of how the power sector is influencing other sectors, agriculture, industry, commerce, and how all these different sectors influence electricity as well.
Is it safe to say, Fernando, that as you start to connect to those other sectors, though, you intrinsically have to lose some level of resolution in your electricity system model itself? So to the greater extent that you start connecting outwards into additional sectors, you start losing your computational ability at the smaller scale, or it loses its meaning to some extent.
That's absolutely right.
Just to zoom back out a little bit, with these various kinds of models, we've been talking about how they connect to other kind of modeling, but just in general, are there some models that, or some types of models, I should say, that are more relevant to different kinds of groups doing different kind of exercises? So some kinds of models might be more relevant to an ISO. Some might be more relevant to a state, one or another of the different state agencies, or to NGO stakeholders. Can you classify them in that way at all?
Yeah, actually, and I think there are actually even some useful examples that are happening out there right now. You know, for example, both PJM, the independent system operator for the eastern eastern and mid-Atlantic states, and MISO, the mid-continent independent system operator that more or less spans from the Dakotas down to Louisiana, are both engaged right now in, I assume this modeling is still going forward, with Clean Power Plan compliance modeling, using a fairly sophisticated suite of tools to look at what happens if all of their states go rate, if all of their states go mass, if they take different, if the states take specific compliance pathways. And I believe in both of those are flowing those from capacity expansion models down to, at least one of them is flowing down to production cost model structures as well, in a fairly specific way, similar to what Fernando was describing earlier, where you really want to be able to look at whether it's operationally going to impact your system or how it's going to operationally impact your system. Simultaneously, I know that a number of the states that are in those two interconnects are also engaged in compliance modeling efforts using a completely different class of model to look at the relative economic benefits of taking different compliance pathways because they have a different series of questions. Those states want to know what's the least cost mechanism for me to be able to comply with EPA's rule while still meeting other constraints that I need to as a state. Some states might actually be asking about job benefits. Some states might be looking at other complementary policies and how those policies impact, or might have different ways that they need to work within their own regulatory structure of the state that's different from what the ISO might assume. So they might want to look at a more detailed suite of policies that are different than the ISO, whereas the ISO wants to know, okay, if we take this mass-based approach, can we actually comply, and will we actually be operating at the end of the day? And so I think they have very different purposes and very different meanings, and both have value.
And we're almost out of time. I'm going to ask one more question, and then we'll close. And let's circle back to the Clean Power Plan before we end up. And let me ask each of you if you could tell me what you think is one of or the biggest challenge for using these models to model compliance with the Clean Power Plan. Jeremy?
Assumptions. It's all about assumptions. All of these models have value. I think knowing what the implicit assumptions are in both a modeling structure, as in what your model is and isn't able to fundamentally do in the first place, and also the value that you attribute to the assumptions that you put into your model, and whether the assumptions that you put in are robust and are testable. So really briefly, one of the things I was noting earlier is production cost models. They're great for knowing how your system operates, but they would completely miss unto themselves compliance opportunities that come out of building new types of resources or backing off or retiring specific types of resources out of your system. It's just something that can't be captured on an operational basis, would be captured on the build basis. And so even fundamentally knowing that you have a model structure that can or cannot capture the thing that will actually lead to a best compliance path for you is one of those, I think, big challenges, and hopefully helpfully answered by this webinar.
Well, I was going to mention the exact same thing as Jeremy. There's a lot of uncertainty looking forward. There's uncertainty around fuel prices. There's uncertainty around technology costs, and there's uncertainty about demand as well. So even if states are required to show compliance to EPA, it'll be great that states can actually run these models on a more frequent basis, so that they can understand how the plans change as all these different uncertainties realize. So I think that'll be important.
Oh. Well, thank you both so much for the presentation. You can see on this final slide here that we have emails for Jeremy and Fernando, so people can get in touch with questions. And we will be sending out the slides and the audio to everybody that's on the call. So thank you all so much for joining us.
Thank you, Liz.
Thank you, Liz.